Cool. So yeah, I'm Kerry and I'm speaking on behalf of Hiverge today. And what I wanted to talk about in this presentation was just going through a couple of interesting case studies where we've applied our algorithm discovery agent, which we call the Hive, on some fairly interesting real-world problems. So just to start with, I wanted to briefly introduce a bit more about who we are. So these are our co-founders that you can see on the slide here, Hussein, Bernardino, and Hamza. And yeah, you might recognize some of these names. These were some of the leading researchers at the team at DeepMind, who were responsible for works like AlphaFold, AlphaTensor, and more relevant to this conference, FunSearch. They were the leading researchers behind FunSearch, and this later evolved into AlphaEvolve, which I'm sure everyone here is at least somewhat familiar with. And so the company Hiverge, we're a startup very much a continuation of the work that was done at DeepMind on FunSearch and AlphaEvolve, led by the very people who essentially kickstarted this widespread interest in this field. And so the mission at Hiverge is to build algorithmic superintelligence and to empower everyone to be able to make breakthrough algorithmic discoveries, no matter who they are. Okay, so to start off with, I wanted to talk a bit about our work that we did on CFAR 10 speedrunning that we worked on about a year ago now. So one of the most important classes of algorithmic optimizations is to essentially make your code faster. So when we're at a lot of conferences, a lot of the time, the first thing people ask us is, "Oh, can you make my code faster?" And so this is a very important question, especially in machine learning, especially with the rising popularity in these LLMs and as they're getting larger and more complex, it's important to train these models as quickly and efficiently as possible. And so something that the machine learning community has done in this direction is to hold what are known as speed running leaderboards. So this is where members of the community collaboratively try and train these neural networks as quickly as possible to reach a certain target accuracy. So on this slide, I've shown two examples of these speedrunning efforts. The first of these is on CFAR 10, so to try and train a image classification network on this data set. And the second one is on NanoGPT to try and train this fairly small, lightweight language model. And so some of you might be more familiar with this NanoGPT speedrunning, since it's essentially the application that auto research was built upon. And so what's cool about these speedruns is that even though they're being done on fairly small or toy examples, they have produced real algorithmic innovations. So one of the outcomes of this CFAR 10 speedrunning leaderboard was the muon optimizer. Um, and although this was initially developed on the CFAR 10 speedrun, it was later used to train the large-scale Kimi K2 LLM. Uh, okay, so these look like fairly nice problems to try and run these algorithmic discovery agents on for two main reasons. The first is that the code isn't particularly complex. The training code for both of these problems is just a single Python script. So that's fairly nice. And the other thing is the optimization goal here is very straightforward. We just want to minimize the runtime of the code. Okay, but one of the main challenges of these problems is that the code is already highly optimized by domain experts. I've shown over here two graphs showing the progress made on these leaderboards over time. And you can see, especially for this NanoGPT speedrunning graph, it's essentially been done to death, especially in this past year or two. And so a question here is, can these algorithmic discovery agents actually make further improvements to these codes? There was actually a paper released by Meta around a year ago, which suggested the negative. They tried using these open source algorithmic discovery agents available at the time to try and even just reproduce some of the improvements that humans have made. Um, and even when these agents were given, prompted with the ideas that the humans have implemented, these systems failed to reproduce the same speedups. Okay, so what we wanted to try and do was to try and debunk this claim a bit. And so what we wanted to do was to get the Hive, again, which is what we call our algorithmic discovery agent, and to try and improve the CFAR 10 speedrunning record. So at the time we were working on this, the CFAR 10 speedrunning record was held by Keller Jordan, who's actually the main person behind both of these speedruns. Um, and he was able to train a neural network to obtain 94% test time accuracy in 2.59 seconds. And so this was done on a NVIDIA A100 GPU as well. So what we did was the setup we had for the Hive was to start from Keller Jordan's 2.59-second record code. And the fitness function that we want to optimize for here. There's a couple ways we could have done this, but at the time, what we landed on was to minimize this, whoops, sorry, this fitness function over here. And what this does is it mainly wants to optimize for the training time, but we also include this soft penalty if the trained model gets a test time accuracy of under 94%. Okay, so there are a couple of challenges that we faced during this project that I wanted to share, and some of the lessons that we took away from it. So the first of these is stochastic evaluations. So when we run the same training code multiple times, the test time accuracy and the training time can both be quite inconsistent. We found, especially with the test time accuracy, this could vary quite significantly. And this was really annoying because uh, the final test time accuracy obtained was quite sensitive. What I mean by this is that trying to improve the accuracy by just a small amount, for example, 0.1%, would sometimes require us to increase the training time by on the order of half a second or so. And so the way that we tried to mitigate this was to run the training script multiple times, which is the fairly straightforward thing to do. And then with the training time, we just took the average. For the accuracy, what we did was we wanted to be a bit more conservative with that. And so we took the lower confidence interval for the accuracy over the multiple runs. And we penalized the fitness function if that lower confidence interval drops below the target 94%. Uh, okay, yeah. The second issue that I want to talk about is quite related. It's where we were evaluating this code on multiple different GPUs. And what we found was for each GPU, even if we ran the same code on them, the results could again be quite inconsistent. So for example, running the same code on two different GPUs could lead to quite different timings. And so for this problem, the way we got around it was by always first evaluating the original 2.59-second code and then using that to compute a relative speed up that future code candidates get instead of using the absolute training time. And we found this was gave us some more reliable results. This third problem, I'm sure everyone is a bit familiar with this one, reward hacking. Um, we saw some fairly funny instances of this during our time. One of these was where the LLM realized it could completely swap out the CFAR 10 training dataset and replace it with a much smaller MNIST dataset. And of course, it could train on that much more quickly. And so, of course, the lessons here were to ensure that there's a clear separation between what the LLM is allowed to do and what it can't modify. Um, but maybe a bit more interestingly, we also found that just leaving instructions in the prompts of the LLMs could help avoid certain cheating patterns. And this worked remarkably well for something that wasn't enforcing strict constraints on what the agent was able to do or not. And finally, one of the problems, the last problem we saw as well was that there was some amount of bias that the LLMs would have on what they focused on. So when we had minimal amounts of guidance, we found the LLMs would often fixate on improving certain parts of the code. So for example, we noticed it did a lot of hyperparameter tuning, but it wouldn't touch certain parts of the code, such as the model architecture. And so what we found really helped here was to help direct the agent to look at certain aspects of the code. We did this either by having a pool of ideas and then randomly sampling ideas one at a time to tell the LLM to focus on. Or we also tried restricting the pieces of code, the sections of code that the LLM was allowed to look at. So for example, we told the Hive to just focus on optimizing the optimization algorithm and seeing how far it could push that when it was focused on that one goal. Okay, so in terms of how well we did, well, ultimately the Hive was very successful at improving the CFAR 10 speedrunning record. So we were able to push down training times down to under 2 seconds, um, which corresponds to a speed up of about 20%. And we were also able to get this fairly nice shout out by Keller Jordan. Uh, Great. So I want to move on to the second case study now. And so this case study is about quantum algorithm discovery. And this was something we worked on together with Continuum, who are a quantum computing company. Okay, so I'll do my best to explain the problem here. I'll preface with this with saying I'm not an expert in quantum computing. But the problem that we focused on here was to try and compute the ground state energy of molecules. You can see this as a fundamental quantity of these molecules, which is quite important to understanding how they behave. But it's a single number that we want to compute. There's a couple of quantum algorithms which are out there which can be used to try and estimate this quantity. And one of the most important ones or popular ones is called a variational quantum eigensolver. So the basic idea of this I've shown in this small diagram here. The idea is that we will represent a molecule in some certain way that we can pass through, that we can give to a quantum circuit, which you can essentially see as a fixed series of quantum operations. And the output of this circuit will be a single number, and this single number will be our estimate of the ground state energy. The idea here is that the better that we design this quantum circuit, the more closely the output of the circuit will approximate the true ground state energy. So we really want to focus on designing as good of a quantum circuit as we can. The key insight into why these variational quantum eigensolver algorithms work is that the value that the quantum circuits can output, this is actually lower bounded by the true ground state energy of the input molecule. So what this means is that no matter how I design this quantum circuit, no matter what quantum operations I put in it, as long as we're using valid quantum operations, this value that it's outputting will never be smaller than the ground state energy. And so what this means is that we can recast this problem as a minimization problem. We want to find over the set of all possible quantum circuits, the one that produces the smallest output. And then once we've found this optimal quantum circuit, we know that its output will be equal to the ground state energy. Okay, that's great. But a question here is how can we actually design these quantum circuits? How can we represent them? Well, nowadays there's quite a lot of libraries out there like Qiskit, Q2Q, or Enquanto. These three, I believe, all have Python interfaces as well. But what's important is that these allow researchers to programmatically represent and simulate these quantum circuits on classical hardware like GPUs. And what this means is that, well, since we can represent these quantum circuits using code, and well, algorithm discovery agents, well, what they do is search over the space of code. They're quite good at doing that. What this means is that trying to find an optimal quantum circuit turns out to be a very naturally suited problem for these algorithm discovery systems. So that's quite nice. So again, what we did together with Continuum was to try and apply the Hive to find new quantum circuits, new quantum algorithms for this ground state energy problem. So the problem with previous or current state-of-the-art quantum algorithms is that they're limited to working on small or simple molecules. Either they don't produce a good estimate of the ground state energy, or the circuits that they produce are too complex, they require too many quantum operations. Essentially, they're not able to run on the current quantum computing hardware that we have access to today. And so what we did using the Hive was to try and explicitly try to discover an algorithm which improves on these VQE algorithms. So explicitly what we did was we tried to find an algorithm which takes as input a given molecule and it outputs a quantum circuit. So I want to emphasize here that we don't produce a quantum circuit directly using the Hive. What we instead do is we try and find an algorithm which tries to use the properties of the molecule to come up with a good quantum circuit. And in this way, we try and hope that we can find a single algorithm which can generalize to multiple kinds of molecules. In terms of what we try to optimize for, there were two main factors here. Uh, the first is the value of the output of the quantum circuit, since the smaller this is, the closer uh, the better our estimation of the ground state energy. But the second factor that we also want to try and improve is the circuit efficiency. So we want to make these quantum circuits smaller or use less quantum operations. And one of the nice consequences of trying to do this is that it'll help these circuits be more robust to noise, which is one of the biggest issues with making uh, modern quantum computers viable. Okay, so onto the results. There's quite a lot to show here, so I'll try and explain what's happening here as much detail as possible. So what you can see here are these green and blue lines. These correspond to the state-of-the-art algorithms, which are called ADAPT and QEB. That's not too important. But then these bar graphs over here, from left to right, these represent the aberrations of the algorithm of the final algorithm that the Hive found. So this left gray bar, this corresponds to the initial algorithm that the Hive started off with. And then this one on the very right, this is the final algorithm that the Hive landed on. Okay, so for this top graph over here, which represents the quality of the ground state estimation, um, anything below this dotted line in this gray region over here, this is what we call is within chemical accuracy. Uh, for us, this means that it's a good enough precision for chemists or scientists to use for modeling purposes, for example. You can see the initial algorithm that the Hive started off with is not within this precision, but the final algorithm is quite comfortably within chemical precision. Uh, Moving on to these other two graphs. So these two graphs both represent some notion of circuit efficiency. And this is where the biggest improvements that the Hive made can be seen, especially for these numbers of circuit evaluations. You can see that it obtains orders of magnitude fewer circuit evaluations compared to previous state of the art. And that's quite important. Overall, we're able to see that it improves it by yeah, more than a factor of 10. And there's a similar story down here with the number of 2-qubit gates. Um, cool. So yeah, just a small summary of what we did here. We also showed the code that we obtained to the quantum chemists at Continuum, and they had this really nice quote about the capabilities of the Hive and algorithm discovery agents. And I think this is nice because it also encapsulates, I think, what a goal that a lot of us here have with these systems. We published a paper together with Continuum, which is in archive here now. And moving forwards, we're also collaborating with NVIDIA Quantum as a freeway partnership to look into future problems in this domain. And just to quickly wrap up, yeah, overall, we've seen how algorithm discovery agent has been applied to two interesting real-world applications. And we're continuing to try and build this technology and apply it to interesting applications. So if you're interested in joining the team, we're actively hiring now. I unfortunately won't be able to stick around for too long after this, but feel free to email me or reach out using our website if you're interested.
Thanks very much, Kerry. It's a really interesting talk. I think we have time for a couple of questions, if you don't mind. So I haven't seen any on the chat right now, but I actually have some questions of my own. So just maybe two things. So the first one, do you guys can you talk about information regarding like the LLM backbone of your agent? Like which model are you using if you're actively fine-tuning or training a model from scratch? And second thing regarding the reward hacking, in my experience, there's a big difference in terms of like how much the model tries to cheat if you give it like explicit access to the evaluator function. So did you guys try to not give it access to the evaluator function, measure how worse it got, and what's your take on that?
Yeah, so I guess on the first point, I can say that at the moment, we're just using off-the-shelf LLM, so we haven't played around with fine-tuning yet. But that's something we're potentially interested in looking into in the future. And then on the second point on yeah, reward hacking, yeah, I believe for the CFAR 10 examples, we were not showing the evaluator to the LLMs. I believe there's been other projects we've looked into where we've noticed that, yeah, like you said, when we do give it access to the evaluator, it does overfit to the evaluator a lot of the time. And so even though sometimes it is useful for these agents to like understand what they're trying to optimize for, um, yeah, something like a real problem is overfitting and trying to balance that.
Okay, thank you very much, Kerry.
Thank you.